right, so let's get started with section 6.8. We're going to look at exponential growth and decay. That's our first formula. Well, it's really not a new formula. It's everything based off of that compounding continuous formula, A equals P times E to the RT power, where the author is just going to change the A to A of T. So he's making this look to be a function in terms of T. So K will be a known value, or we'll have to go find the K value first. Capital P, our principal, has been changed to capital A sub 0, which means this is the amount at time 0, which basically says your beginning principal, so it still means the same thing. And they switch out the R with the variable K because now they just want you to know that if your K value, your rate, is positive, then you have exponential growth. And if your rate K is a negative value, you have exponential decay. 6 of one, half dozen of the other. I don't get it why they changed the variables. I'll probably be writing this down because I'm so used to it. Newton's law of cooling, this function states that you're going to have capital T, which is the constant temperature of the surrounding medium, otherwise known as room temperature, and plus this binomial here, U sub 0, that's going to be the initial temperature of the heated object, minus the room temperature, times e to the kt power. Well, again, if this is going to be cooling, your k value has to be negative. All right? So again, just remember, you can have r is greater than 0 as growth. You can have r less than 0 be decay. You can still keep the same r. That's all good. Oops. And over here, our temperature has to be decaying because it's cooling off. So your K value has to be 0. Again, surrounding medium is your room temperature. Initial temperature is your oven temperature. All right. So first example. A colony of bacteria grows continuously, okay, A equals P times E to the RT power, at 4.5%. It's growing, so that means your rate is going to be positive. So again, basing it off of this formula, if you want to write it in your function notation, that's fine too. It's all good to me. The colony starts with 100 grams. Okay, that's going to be your P or your A sub 0. Write a function for the growth where N is measured in grams and T is measured in days. Okay, so N, that's going to be replacing the A. N of T equals N sub 0 times e to the RT power. But we know what R is. It's 0.45. Just bump the decimal point 2 places to the left. And we know what our starting value is at time 0 is 100 grams. So there's my function. Here they're asking us to graph the function on our calculator with the following window. So this is your x min, this is your x max, y min 0, y max 400. So I'm typing this in to y1, 100 second ln, raise it to the 0.045 x power. So we'll put an x instead of a t for our calculator. And we'll graph it with that window. There's my picture. So what is the population in 5 days? Okay, so you just have to type in trace, type in a 5, hit enter, and it's going to crunch the value for you. 125.2 grams. How long will it take for the population to reach 150 grams? Okay, you can do this one of two ways. We could take N of T, make that 150, and solve it for T. All right, got to get the base E by itself, divide over the 100. That makes it 150 over 100, or if you actually wanted to divide it, you can change it to 1.5. We're going to take the ln of both sides and simplify it. So like I said, 150 divided by 100 is 1.5. ln of that fraction equals ln of this, ln of, and e cancel out, or you can say we're using the conversion rule. But either way you look at it, you get 0.045t. Divide that over to the natural log. Enter it into your calculator in your home screen, and we're approximately 9 days. Now, we could also do this with the graph that we already have here. You can go back into your y equals screen, change y sub 2 to 150, regraph it, and find out the intersection. So just hit second, trace, go ask for the intersection between the two curves, and it gives you that answer, 9.01, same as if you did it on the home screen. Next, how long will it take for the population to double? Well, that's just like the top problem up here. It's just that we're putting in 200 instead of 150. So 200 divided by 100, we'll have 2 right here. Then we'll convert it. Natural log of 2 equals 0.045t. Divide over the 0.045. We get 15.4 days if you work this on the home screen. Or again, we can go back to our y equals, change that 150 we just put in, and change it to 200. Find the intersection, and there's the same 15.4 days. All right, so that was continuous growth. Here's a continuous decay problem. In 1980, the population of Detroit, Michigan was 1,203,368. In 1990, the population decreased to 1,027,974. If the population is modeling exponential decay, find the following. What is the population decay rate? All right, so we need that formula we discussed. Again, you can put A equals P times E to the RT power. That I'm perfectly happy with. I'm just following what you might see in an example in my math lab. So in 1980, that was times 0. That's our beginning year. And therefore, this is A sub 0. In 1990, now T is equal to 10. And this will be A sub 10, the population in 10 years. So we're going to throw this all into our formula right here. So A sub 10 equals the beginning population times E to the K times 10. And then we're going to take out this A sub 10 and replace it with the 1,027,974. Don't worry about how big the numbers are. We're going to let the calculator deal with all of them. Divide over the 1,203,368. Now that's equal to E to the K times 10 power. Well, to solve for K, take and convert it to a natural log, or take the natural log of both sides. 6 of one, half dozen of the other. It's the same thing. Natural log and base E cancel out, leaving me 10K. Divide over the 10. Cancel my 10s on the right. There's my calculator entry. This is my rate as a decimal. And notice it's negative. If it's going to decay, you have to have a negative rate. So if they wanted you to convert this into a percent, it would be 1.5753%. Round to wherever they ask you to round. So if we had to write the exponential model for P as P of T, where T is the time in years after 1980, we're just going to take this, round it to maybe 5 decimals, 4 decimals, again, whatever they ask us, and plug it back in for K, and leave your function in terms of T. So A of T is equal to that beginning population, 1,203,368, times E to the negative 0.01575 T. So what is the estimated population in 2020 based off of what happened, 40 years ago, 30 years ago? Well, in 2020, that'd be 40 years after 1980. Take 40, plug it into our function here. Go to our calculator, crunch the numbers, 640,903. That's almost half the population is gone. Now, what was the actual population in 2020? Well, according to Wikipedia, Detroit's population in 2020 was 639,111. Almost right on. About what? 1,800 off? 1,800 people off? That's a pretty good estimation when that was 40 to 30 years prior to the actual population. All right, now for my cooling problem. An object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. If the oven temperature of the object is 80 degrees Celsius after 5 minutes, when will the temperature be 50 degrees Celsius? So using Newton's law of cooling, we want to start identifying everybody here. All right, capital T, that's your room temperature, 30 degrees. U sub 0, that's the oven temperature. An object heated to 100 degrees, that's your oven temperature. So we're going to substitute those values here, here, and here. Simplify that. 100 minus 30 will be 70 times my e to the kt. Next, we have to solve for k. We have to find, if you will, our decay rate. So it says our object will be 80 degrees Celsius after 5 minutes. So we're going to put 5 in for t and set this equation equal to 80. And what we're going to do is we're going to solve it for k. So the first thing we got to do is work to get this e to the k times 5 by itself. So we're going to subtract over the 30. That gives us a 50. And then we're going to divide over the 70 to get the base e by itself. And then once we're exponentially by ourselves, you're going to convert it into a natural log. So the natural log of 5 over 7, all I did was just cancel the zeros, is equal to the exponent, 5k. Divide the 5 over, go to our calculator in the home screen, natural log of 5 divided by 7, close the parentheses, divided by 5, approximately negative 0.0673. And again, my math lab usually goes to 4 decimal places with the finding of the rate, the decay rate or growth rate. So we found k. Let's go take it and plug it into our formula right there. Now we can answer the last part. When will the temperature be 50 degrees Celsius? So 50 degrees Celsius, that's going to go in for u of t. And now we solve for t. And folks, it's the exact same steps, except at the bottom we don't divide by 5. You now divide by this rate that you found for k. So again, subtract over the 30. Notice it's the same. That's 20. Divide by 70, the same. Convert to a natural log. Now instead of ln of 5/7, it's ln of 2/7 equal to negative 0.0673. We're going to divide that over, and that's going to be approximately 18.6 minutes. All right, next we're going to take this formula that we've acquired right here. We're going to go graph it. So if we graph that function in the following window, 0 less than t less than 60, again, this is your x min, this is your x max, 0 less than u of t, that's your y, less than 120, y min, y max. So I'm going to enter this in to verify my answer. So we're going to put 50, all right, just to double check, what was the 50 for? When will the temperature be at 50 degrees Celsius? We're going to verify that this is correct. So I type it all in. There's my x for the t. I graph it. And I need to find this intersection. Well, one thing I did real quick is, if you think back to the above on the problem, it said, remember, at 5 minutes you were at 80 degrees Celsius. Okay, 79.998. We're right on target. Now, why isn't it exactly 80? Because we rounded our rate. So we intersect this. There's my 18.614606, just like we got in the last part of the problem. All right, so again, second trace, do the intersection, just hit enter on all three questions. They're all right there for you. So what is the elapsed time before the object is 35 degrees Celsius? Okay, let's go back to the calculator. Change your 50 to 35. Regraph it and re-find the intersection. This would be 39.2 minutes. What is happening to the temperature as time passes? Well, if you think about the formula right here, this is my constant. Think about your transformation rules. Your horizontal asymptote went from 0 to 30. It has to approach room temperature. So I changed y2 to 30, graphed it, and you can see the curve is completely above the line on your graph. All right, so that wraps up our 6-8.